In this video I will show measurements of sideband noise using Linrad, and I will start with the simple measurements and continue to sophisticated measurements later on in this video. I have pairs connected to my computer, and I have set it, as you can see here, for a 250 kilohertz bandwidth. And I start in SSB mode, pressing D. And I haven't run this before, so I select to use the default parameters. Just press any key. Enter several times, and here it starts, and the frequency should be about 14.15, because that's where this oscillator is. And here is the spectrum. It doesn't look good. If I press A, I can see that it is saturated here. So I use the attenuator to adjust the level. That was 10 decibels attenuation, and you can see I have 19 dB amplitude margin now. Sorry, it was 20 decibels, so I increased by 10. Now it's 8, and I remove 2 more decibels. Now this is the maximum level I can have with the passives. If I add 1 more decibel, it starts to show 0. And that is a peculiarity of the passives system. This is related to listening at frequencies below the sampling rate. I have clicked on the signal, and here is what the baseband looks like. And you can see there are many spurs here, and they are because the parameters I selected is a compromise, not intended for sideband noise measurement, but for low processing load in case the program would run on a slow computer. I changed the window function for the first FFT from 2 to 9. This will remove, or at least attenuate, the spurs very much. The transform size became twice as large, so I asked for 200 Hz instead to get the same settings for the wide band graph. And then I take the left as the standard. And here is the function now. And you can see there are no visible spurs here. They should appear at the same separation as they did before. And that is because the first FFT size is the same. Those are resampling spurs because of inadequate filtering, and that is typical for a digital receiver. It can be optimized for speed or filter accuracy. With these parameters, there are artifacts in the baseband graph if you make it as wide as possible, which I did now. So to do any reasonable evaluation, I just expand it once, twice, and here I can trust the center part of the baseband. I set the bandwidth to about 1 kilohertz, and then look at the signal level graph, the S-meter graph. I set it to show dB per hertz, and then I calibrate the level by clicking it like this, and you see it shows 32.567. So I enter 32.567 here. When I now evaluate, it shows the level is 0 here, and that is to set the level of the carrier. And then I click, let's say about 10 kilohertz up, that's here, and then I can read the noise here. And I don't want both traces. The white is the peak level and the yellow is the RMS power. So that is mean value of power. And here I can read minus 147.9 dBc per hertz. And I can also read the power is 117.7, and 1 kilohertz bandwidth I have to add 30 dB. That's why it becomes 147. I can set a narrower bandwidth like that, and then it runs slower, and the power is outside the graph now. So I move things, and here is the noise. It's much weaker, but when I evaluate, it still shows minus 147.9 this time. So this way I can look at the noise much closer to the carrier. I changed the beat oscillator frequency to make it show 15160, B for BFO, and I press plus to make the step size larger, and then I can move the frequency. Like that. And minus to make it smaller. Well, this is good enough. And you can see here how the apparent bandwidth, the skirts here, how they vary depending on the frequency with respect to the dots on the curve. I mean the frequency bins of the FFT. This is an artifact of using the sine squared windows. It's related to the problem that I saw before with the spurs when using that function for the main spectrum, the first FFT. Anyway, this is what we have, and I step from 160.0 to 160.1. Sorry. Somewhere here. And I change this one to change frequency instead, means tune. So I tune. Now I am 1 kilohertz up in frequency, and I have a fairly narrow bandwidth, so the slope that I can see here doesn't matter. And I try to run a little faster. And here the level is minus 138.9. let's say minus 139. I have connected now a free running oscillator. It doesn't have any fixed capacitor on the resonator, only a capacitance diode. So it takes some time before the frequency is really stable. It's clear that it's more noisy here than the other one was down there. It's just disappearing. And the frequency is stable enough now to allow me to do a measurement. It shows 14165.56. Well, I have to wait just a little bit more. The unit is still drifting, and it is rather microphonic. If I tap on the table, that is what happens. So I add some mechanical isolation, vibration isolation. I put it on some plastic foam that isolates, so now it looks much better. But if I tap on the table, it still looks like this. So much better, but I can isolate more. This black thing is rather heavy, so the mass is now several times higher than before. It doesn't make much of a difference. You can see my voice when I'm speaking. That is vibrations through the air. But if I tap on the table, like before, well, no big difference. So maybe transmission via air is the most important. Now it doesn't matter for measurements at the 1 kHz separation, and it has drifted far away enough now, so I put at the center the cursor, and then I can see the level here. If I wait long enough, here it shows now minus 0.06. So I do not make any recalibration. This is accurate enough. And I read the frequency, 164.18, and I want then 165.18. That's here. And then I can wait for a while before I read the sideband noise. And it's much higher than before, because I did change here from, I think I had 5 and now it's 35. So that is a difference of 30 decibels. And I see minus 119.6. So what I see is 20 decibels more noise than I had with the reference oscillator. And with the reference oscillator, the noise was probably coming from the passives more than from the reference oscillator. That will be clear later on. And I don't remember exactly what the levels are for these units. This unit is a similar oscillator, but it has a common design error. The capacitance diode is fed through a fairly large resistor, and that means that the noise of the resistor, thermal noise as well as the noise due to the leakage current through the diode, they create a noise voltage that makes the frequency noisy. I have to wait quite a long time for this to stabilize. There has been some small drift in amplitude, so I change calibration again. It shows 0.014, that's accurate enough. And the frequency for the center is now 14.168.1. So I want 169.16 or so. 169. Oh. About here. And you can see the slope is now significant, even though the filter is so narrow. And here is the level. I have to wait a little. And it's drifting downwards slowly because the oscillator is not very stable, and it is drifting away from the 1 kilohertz. But this is accurate enough, minus 93, and I don't want to give a decimal anymore. Here is another oscillator with a common design error. It is a good crystal oscillator followed by an amplifier that has a high impedance on the base of the amplifying transistor, or maybe the gate. I don't remember if it is a FET or a bipolar. Anyway, high impedance at audio frequencies. And it looks like this, and it has already stabilized well enough in frequency and also in amplitude. So I can step up 1 kilohertz. It says now 62.08, so I want 63.08. That's here about. And the noise floor is flat here. And I have to wait for the level, not very long. And here I see minus 133.6. So these are the results with the Perseus measured the standard fashion with an S meter, just at 1 kilohertz offset. And these 4 oscillators of mine that I have designed to test these sideband noise measurements. And I have written a page on the internet about them and measurements on them with better methods than what I have shown here. And it's this site, and you have here some measurements, professional, and some measurements with notch filters. Now I'm looking at this oscillator, and that is with 2 SDR-IP units, both of them phase locked to a 10 MHz reference. I have set the levels so I see properly 0 up here, and then I shift the frequency by 1 kilohertz by clicking 1 kilohertz up in the waterfall. So that makes the frequency jump, and then I get the noise at 1 kilohertz offset like this. 139.3 and 140.4. They are a bit different, The reason will be obvious later on. I have connected this oscillator now, and as you can see, it drifts quite a lot when it starts. But this is a rapid measurement, I don't have to wait very long. I have connected this oscillator now, and as you can see, it drifts quite a lot when it starts. But this is a rapid measurement, I don't have to wait very long. Properly set level, and I shift by 1 kHz. First I move it to the center, it's here, and 64 and 2.7 about. So it is here. 1 kHz away. And here I have minus 119.5. Now I'm looking at this one, and it is very noisy, as you can see. I haven't changed any of the settings, and it is visible that it is unstable. And I have set the level right, and again I click 1 kHz up. That will be about here. And here I have the noise floor at 1 kHz offset. Minus 93.7. And finally I look at this one, and I have set the level properly. I have to check because it's easy to forget things. And then I jump 1 kHz again and look for the noise floor. And it says 133.6 or 8. And it's a little bit different between the channels. These are the parameters I have been using. I will change them now because I'm going to enable the correlation spectrum. And I will go to mode 1. And I have to set a much narrower bandwidth for reasons that will be obvious later. Let's say 10 Hz. And then also first FFT window, I make it 8. I have again connected this new ref oscillator. It showed minus 140 before, so when I look at it here, properly calibrated, and I step it 1 kHz, that's here, and I get the noise floor exactly as before, and it says minus 140, and that's no surprise. But here you have the correlation spectra. The yellow trace is the average of 100 correlation spectra, it's the number here. The green trace is the average of 2,700, 2,800, and the expected gain of having so many correlated spectra taken average of should be 17 dB, and the observed distance between the white and the green trace at this frequency is 18 dB or 17 dB. I have to wait a long time to see where this ends. After about 24 hours, I have 709,000 averages. I check the amplitude. I put the signal in the middle of the filter and I check here. And the level hasn't changed. I didn't change the calibration since yesterday. And then I step 1 kHz away. like this, and look at the noise floor. And 139.96, that is minus 140. And the advantage due to correlation is 26.8 dB. Very close to the theoretical limit 29.2, so probably the unit is a little bit better than what I can read. 140 plus 26, that is minus 166.7. I can step in steps of 200 Hertz, like that, and look at the correlation advantage. Here it looks like 23 decibels with a theoretical limit of 29. So it means that what I read at 200 Hertz offset is 134 plus 23, that is 163. And I step 200 Hertz more. Like that, and the noise goes down, of course, and the correlation advantage goes up a little. So if I step 200 Hertz step size again, that's here, the correlation advantage goes up and the noise did go down a little. And I continue to step further up. Suddenly there is a frequency which is bad. And I don't see anything in the waterfall graph, but I can expand the waterfall, the main waterfall here. And now we can see there is a signal at this point. You see this green peak. And if I expand more, it will be more clear. There are spurs here, several of them, and they are well below the noise floor, so they are absolutely not visible in the baseband. But I see them when measuring with the correlation technique. And I see this structure, it's also a spur. These are correlated spurs in the SDR IP. Both are locked to the same reference frequency, so there are synchronous features. I have looked at these things in the Nerds series of videos if you are interested to get an idea what is behind this. Anyway, what I'm looking for is now the performance at 1 kilohertz. And here is what I have seen so far. Now we understand why these differs so much. That's because these numbers, they represent the noise floor of the SDR IP. The noise of the oscillator is far below by 25 dB or something. And for the same reason, this oscillator is too close to the noise floor of the SDR IP units. They differ by about 1 dB. Here the difference is 0.2 dB because there is some noise from this oscillator. I clear the correlation spectrum. When it reaches 100, the yellow has gone up to its steady level. The green is at the same place when it counts to 100 here. And if I wait a little while, I see the noise from the oscillator is stronger by far than the noise from the noise figure of the SDR IP. So all the curves coincide at 1 kilohertz separation. And I have to go about 20 kilohertz to get 2 decibels advantage from using the correlation. So there is no reason to measure these oscillators, the other ones, this, that, and that, with this method of measurement. I'm looking at this oscillator again, but now I have set the first FFT bandwidth to 2 kilohertz, and still I'm using the Gaussian filter. And I can clear the correlation spectrum, alternate Z, and you see now it is going far quicker. The collection of averages is much faster because the bandwidth is larger. So I have lost the possibility to see the narrow band spurs, but I might see something with many more averages that I collect in a reasonably short time. So I will wait for maybe an hour or so. Calibration is restored. It has changed a little when I changed the bandwidth of the first FFT. Now when I click 1 kilohertz away, like that, you see I have a spur here. It's a resampling spur, which has to be avoided when I evaluate the noise floor. But by doing it properly, I can just check here, and I still have minus 140 dBc per hertz. And there is zero correlation advantage, because that is evaluated as the difference between the white and the green curve, and I cannot evaluate that with a 2 kilohertz bandwidth. But I can look at some larger separations, let's say 10 kilohertz. And here the theoretical is 28, but I observe 24. So I make little changes, because sometimes I happen to come on spurs. Now I have collected more than 11 million averages. The theoretical limit is 35 decibels. On the peak, there is no correlation advantage. Of course, all the curves are on the same position within the filter, and the level is still calibrated. When I look at the separation between the white and the green, it is much smaller than the theoretical 35 dB limit. So this means the green curve represents a signal that is correlated between the two SDR-IP units. It is probably digital noise within the SDR units, because it couldn't be the noise of the oscillator, because when I measured it long ago, I found that at 20 kilohertz it's at about minus 180 dBc per hertz. This was this article, where you can find how this value was established. Maybe the correlated noise I see here could be due to rounding errors in the FFT, because FFT1, the first, is done with single precision floats. Now there is an alternative to select double precision, so I will do that. I have saved this image and I will run with the double precision to see whether that makes any difference. That is first forward FFT version number 6. Now I have collected 81 million averages, and the theoretical limit for the correlation advantage is 39.5 dB. But what I see is 27. So this is clearly the correlated noise of the STR-IP units. And with this resolution, 2 kHz, it looks pretty flat. There is a structure here, and there is a structure here. If I click on the carrier to check the level, I see it hasn't changed, of course. And then I can click 20 kHz up, where I know the oscillator is at minus 180. And here I read 150. And add 27, that is 177. And a half here and a half here, 178. So that differs by 2 dB from what I expected. And it is very flat. Now I can compare with the result I had with the single precision Fourier. It looks like this, and it's very similar. The level didn't change. Here is the old measurement, and here is the new one. And you can see this is more noisy, but the level is the same as here. So I cannot say that the double precision made any significant difference. With the wide bandwidth, I have these resampling spurs. So if I click on one of them, I move it to the center. Then the next spur comes with the same position because they have they have the same distance between them. So one more, and one more, and one more. Now I am on the skirts here. One more. And now it's very weak. Now you can see here is a weak signal that can be observed. It is visible because the resolution is much higher in the baseband. If I click at the center of this peak, you can find that this is the signal. But it is about 15 decibels below the noise in 2 kHz bandwidth. It is visible, but it's still below the noise. You cannot see it here. But signal plus noise is a little bit more than noise only, so it can be seen. I will now do something that isn't really good to do. I change from 1 to 2 on the enable correlation spectrum, like that, and I don't change anything else, not yet. I have to set a large storage time for the baseband in order to be able to collect many averages, and also to make the transforms bigger so I get better resolution. So I set the maximum value here. And here comes the phase noise spectrum. The offset is here, 500 Hz, 1 kHz. At 2 kHz there is a big spur. It is the resampling spurs that come because I have a very wide bandwidth on the first FFT. It is visible, some of the dots here are blue. They show that the real part of the correlation spectrum is negative, and yellow dots, that's when it's positive. The red dots is the absolute value of the imaginary part. So it comes the same regardless of the sign. Now the imaginary part is at the same level as the yellow, as the real part. So it means I'm just seeing noise. I don't see any correlated signal. So I have to wait. This is only 300 averages, and that is in 1 minute. I am detecting the phase noise and also the AM noise with a quadrature detector. You can see some odd phenomenon here. That is because I am extracting the carrier to use for the quadrature detector by picking a signal within this filter. And this filter is not so very narrow. I can expand the scale to make it visible better. So it is about from here to here. That is about 200 Hertz. That's why you can see here the noise, which is about 200 Hertz wide. I think that's the reason. And it also means that probably the result I can see close to the carrier here is not accurate. I have to go to at least 200 Hertz, 300 Hertz. Here I get the correct reading at 300 Hertz minus 165 or so. And this is the phase noise. Here is the amplitude noise. And now I am interested in the noise at 1 kHz to compare with the previous measurements. And as you can see, the white trace and the red dots are on the same level. So it is below minus 165 at least. And here is amplitude noise as well as phase noise. So the phase noise is much lower than the amplitude noise. And this I didn't know previously. It shows minus 172 on the phase noise. But when I look here, you can see that the phase noise is the phase noise is not reliable because the imaginary part and the real part are at the same level. So I have to wait. 4.5 hours gives me the noise at 1 kHz here as minus 173 dBc per hertz. You can see the peak that came there. I was a little bit careless, and that explains the structure you see here as well as this little peak. This was some noise that I made. This measurement is extremely sensitive, of course. So there is some microphonic action, even though I have this vibration isolation from foam plastic. I switch for the amplitude noise. As you can see, the uncorrelated noise is much higher. So the real part and the imaginary part are equally strong, which means I haven't reached the noise floor yet. So I cannot judge what the level might be. If I plot both of them, you can see here, at 1 kHz, the difference is almost 10 decibels. I have now connected this one again, and I clear and wait. And as you can see, all the curves are on the same level, and that is minus 118.5. Well, I can change the scale to read more accurately. Well, at 1 kHz, I can read here 118.7 for the phase noise. The amplitude noise is much lower. 1 kHz here, that's about minus 149. And the phase noise again, I cannot see it without changing the reference level. and it comes here minus 119. But I have to repeat it again because when I touch the keyboard, that causes vibrations that destroy the result. This is microphonic and the measurement is extremely sensitive. So I clear this again and then I wait without, well, if I shout, you can see that comes up something. I start once more and I keep quiet. So this is minus 119 for the phase noise. Here is the oscillator with a deliberate and not uncommon design error that causes AM noise. And this is what I see. It runs fairly rapidly because the noise level is high. It tells me AM noise minus 134, phase noise minus 149. This is the oscillator with a common error that causes phase noise. A resistor instead of an inductor to connect to the capacitance diode. And here is what I see on the screen. Phase noise 93.3 maybe, and amplitude noise 108.7 about. And this is with a lot of averages, far many more than what is needed. If I look at here, you can see the reason why the yellow trace is above the two other traces is that I have made some vibrations on the box and then it gives something which is not present in the latest 250 averages. And amplitude noise, it looks like this. Amplitude noise can be reduced by use of limiters. I have made this setup. The box I'm calling AM with phase noise minus 149 and amplitude noise minus 134. I will show what happens when I do this. Oscillator, 6 dB gain, 6 dB more gain, a low pass filter from mini circuits, 15 MHz, the limiter box with crossed diodes and capacitors in it, and then a second low pass filter from mini circuits, and then I use this unit to set the level near saturation for the SDR IPs. The phase noise is now minus 148 and the amplitude noise is, well, a little bit more better than minus 148. I will wait a couple of minutes. The phase noise is about 147.7 and the amplitude noise 148.5. I have replaced one of the low-pass filters with this series resonator. Just an inductor, 6.8 microhenries, and a capacitor to tune it. What I see is this. And it's immediately clear it is much better. It is below minus 151 or maybe even 152. This is the phase noise. The amplitude noise, that will take more time, so I have to wait for it, but it looks like it is still at minus 148. Well, the phase noise is now minus 152. It has improved significantly. And the tuning of the series resonator is critical. It should not be tuned for maximum signal, just a little bit more capacitance than needed for that. And the amplitude noise is minus 148.3 or something like that. The obvious explanation is that the transistor, which has a lot of low frequency noise current in it, that produces a lot of amplitude modulation, but it also produces some phase modulation. So by use of this limiter, I can produce the appropriate phase modulation when it is cutting the amplitude of the signal. So some of the phase noise introduced by the amplifier is cancelled. So this is something to think about, maybe in future designs of oscillator. There could be a reason to look at the tuning around a limiter to optimize the phase noise. So this was the oscillator itself. And now with this series resonator, I observe these things. And the improvement is 3 dB on the phase noise and 14 dB on the amplitude noise. So this is something to think about sometimes. There are some things to worry about when setting parameters for correlation mode 2 in Linrad. I have now a large bandwidth. That is not normal, but I have it to demonstrate some phenomena. I'm using the Gaussian window now, and there is nothing special otherwise here. Then I set the minimum bandwidth reduction, that is 2 here. The reason for that is to see as large bandwidth as possible on the correlation spectrum. And I set the third FFT power to 8, which is the Gaussian window. And by baseband storage time, I set that to maximum. That is because that parameter determines how many averages I can have of the correlation spectra. And this is the screen that appears. I click near the peak, and you saw perhaps that the signal drifted into the center here fairly rapidly. Now, one thing to worry about is to make the bandwidth adequate here. It is now fairly narrow, but not really narrow. I will demonstrate the problem by just making the bandwidth much larger, like that, and then clear. And now you see I have a problem here, an artifact of some kind. I can make the bandwidth even wider than this. Now it is 1.5 kilohertz. And then I get artifacts up to about half that frequency. So, and this is obviously something to expect, because the detector is a multiplication of the signal that passes through this filter with the entire baseband signal. So it means the noise that we have here, including my voice, that is going to be used in the detection process and add or remove from the spectrum. So to get a reasonable reading, I have to make the filter narrow, but not narrower than that most of the signal, the real signal, which comes from here to about here, is in the flat region. So here is the spectrum, and the width of this is maybe 300 Hertz from here to here. So I should not trust what I observe below 300 Hertz or so. Because sometimes the carrier drifts, and now it is at the side of the filter. And it will adjust itself if we wait long enough. So I can increase the filtering here, but before I press T to look at timings, we have 15% CPU load. I increase the transform size, and now it is 27%. And once more, 54. Well, going above this is maybe not a good idea. So this is the narrowest bandwidth I can have. And you see there is something that I don't want to include in the filter bandwidth. And I clear the spectrum here. And now we should be able to trust what comes that is within about 100 Hertz. So that is 1 kilohertz. I have to make the transform bigger here. And maybe I can expand the scale a little. So here is the noise up to 100 Hertz. It may be okay a little bit more. The peak here is this peak, I guess. Looks like 50 Hertz. Not very surprising. And of course, if I make this bandwidth a little bit wider, like that, now it's 200 Hertz. The 50 Hertz peak has disappeared. And all the other most of the other noise here also. And I can make it a bit narrower. And still I don't see the 50 Hertz spur. So in order to get a narrower filter, I cannot expand here probably. I can make a try. Linrad may crash like this. It says it cannot start the output. That's because the CPU is overloaded. With the parameters I can read the noise sideband up to about 8 kHz. As you see, the noise goes up again here. That's an artifact. So maybe I should say rather 6 kHz. I'm not sure. Maybe someday I will remove this artifact. Well, the way to get a look at the closer frequencies is to change some parameters. Namely, the first mixer bandwidth reduction in powers of 2. So I set it to maximum, that's 5. I have the same filter, but now the powers of 2 is 10 rather than 13. So the CPU load is very low, the baseband speed is lower, and the transform is smaller. So I can expand here. And now I can make the filter much narrower. I don't make many averages anymore. I take one transform at a time. And you can see how it is drifting. And this drifting is actually phase noise. And sometimes it goes outside the filter. This doesn't work with this oscillator. The phase noise is too large to try to measure within a 10 Hz filter bandwidth. So very noisy oscillators, we will have to be happy to see that in a wider separation. But I will connect a better oscillator, and then this will be stable and one can do measurements closer to the carrier. This oscillator is a bit better, but it's not very stable. You can see it's drifting. If I left it running for a longer time, it may drift slower, but it wouldn't stand still. The coverage now is only 1 kilohertz, not even that, 800 hertz perhaps. But I can go as close as 10 hertz from the carrier. So I have to set a much larger transform here. And that makes it very slow. Well, 10 hertz here. I could make it 14 instead. 10 hertz, it's here. So it takes time now. After a while, the frequency drift has slowed down enough. So I have been able to set the bandwidth to only 2 hertz, or even slightly below that. And then, of course, I have expanded the spectrum so I can read down to 2 hertz here. And now it's obvious that below 5 hertz, the noise is high, so the imaginary part is already well below the real part. So at 5 hertz, the noise floor of this oscillator is minus 105 dBc per hertz. And you can see how it walks. It's the random walk region of the oscillator where the noise goes rapidly up as frequency comes closer. Now it has been running overnight, 9 hours, a little bit more, and I have a good noise spectrum for the sideband noise from probably 1.5 hertz, because that's the filter bandwidth I have now, up to about 35 hertz. I can look at a higher offset by changing the scale here to, let's say, 0.2. And then you can see that I can probably trust the results up to 200 hertz. But there is some problem here around 50 hertz. And amplitude noise, it's lower, so I can only trust it up to maybe 40 hertz. And if I want to look at the close range, I put, let's say, 8 here. And here is the AM noise, and it is maybe not accurate at 1 hertz, but at 1.5, I think I can trust it. And the phase noise, well, here is AM noise and phase noise. And you can see here, this is the artifact of having a too wide window, too wide here, but
I cannot make it narrower because the frequency is drifting. Here was a frequency correction. You can see the white line over the entire screen. And it has shifted by 0.3 hertz or something. So from here, I have a good, very accurate, because the imaginary part is far below. So 90 decibels at 1.5 hertz. This oscillator has a traditional $50 fundamental crystal. If I want to see the higher frequencies, I would run another instance of Linrad over the network, setting a wider bandwidth, and then also a smaller transform here. And then I could collect 10 times faster, or even more than that, to get the range high, the offset range a factor of 10 higher than this. And the total CPU load here in the left corner, it says 3.9%. So there is no problem running several instances of Linrad at the same time on this computer. But one thread is loaded up to 53%. Is this one, 52.7. So I cannot run this graph with more load. When running with a very narrow filter in the baseband, there is a problem caused by the fact that Linrad was written for a single-threaded application using SVGA lib for the mouse. So it doesn't have a separate function that is interrupt-driven. So if I want to see, for example, how the carrier travels in frequency, I would change here. And to change, it is not enough just to click. I have to press the mouse and hold it down until I see a new update on the screen. So I press the mouse now, and now I can release it. And then you saw it took some time, and now I can type a new value here. And I type, let's say, 60. And then I press enter. And here you can see how the frequency goes up and down. And you can note the amplitude. I can do that by expand, that is this button. And it will take some time until you get back the entire trace. I amplitude the frequency variations. That way. And you have the time on the left-hand scale. The time here. So here one can analyze the frequency drift. Now, that is not the frequency drift of the device under test. It's the sum of the frequency drift of my reference oscillators and this test oscillator. So there is no correlation in here. This 10 MHz oscillator is commercially available. I have connected it, but I have to change the frequency to 10 MHz. 10. And here it is. And I click on that. and I press A to see the amplitude, and as you can see I have a 12.7 dB amplitude margin, so I need to reduce the attenuation by 12 dB. Something like that. And then I clear the amplitude. Now I have 0.96 or 1.5 dB. So I can clear the graph here and wait. And the result is far away from what I expected. This is because I did something which is not proper. I have to reduce the transform size, means increase the bandwidth. So I press here, and now you see I have clicked on a spur. It happens to be at an offset of 20 Hertz. So I click on the carrier here, and now I can do a measurement. This spur at 10.0 is because of my reference signal at 10 MHz that controls the frequency of the box. So I can clear again here. And now I can see the spectrum, but the bandwidth is not as narrow as I want. I expand and increase the transform size again. And now I want to decrease the bandwidth. So I press on the yellow vertical bar, and I have to keep the mouse pressed for a while, and then I can move it. And then I release the mouse and wait for a while, and now I can move the mouse away. And I could wait for Linrad to adjust the frequency, but I can press the mouse in the waterfall here, and then when I release it, it should jump if I waited long enough. So I did. And now I get the measurement, and the bandwidth I have here, from here to here, is about 0.7 Hertz or so. And I wait for a while. This has been running for 1 hour now, and I can read performance up to 3 Hertz or so, where the separation here is good enough. So 1 Hertz minus 108, and 2 Hertz minus 116.5. Now, these numbers do not agree with what I have seen from a commercial instrument on this same oscillator. Maybe the resolution that I'm using is not good enough. Considering the very steep slope here, it might matter. So I will change the resolution. I go from the transform size 16 to 18. That means 4 times larger. So I change the X gain from 8 to 2. And now it will take 4 times longer time to collect the same number of averages. As it turns out, this didn't work well. I don't know the reason, but there is a workaround. I reduced the bandwidth from 2 kHz to 500 Hz here. And then I can change the bandwidth reduction. Now I can put 7 there instead. Minus 108 dBc per Hertz at 1 Hertz. This is what I see now, and it is after 6 hours. What I had before is here, and there is no difference at all, although the number of points in the transform is different. Look at the peak at 5 Hertz. Oops. It has disappeared. So it was a spur generated by resampling, presumably. At 5 Hertz I see 125.5. This particular oscillator has been measured with a professional signal analyzer, an Agilent E5052B. The results are a bit surprising. It starts at 1 Hertz, and there the result is minus 102.4 or 5. That's a difference, a significant difference. You can see here, at 5 Hertz, I see minus 125. That's the same that I saw, minus 125 and a half. So it seems that this instrument is not so accurate at very close separations from the carrier. At 10 Hertz, I see 131.5, and then it starts to become noisy at higher offsets. That is because of the high noise, sideband noise of the SDR-IP units at 30 Hertz or so, but at higher offsets, let's say 100 Hertz, the SDR-IP is much better. So I can see here minus 143.2 or something like that. And at even higher offsets, something is going wrong, as you can see here. I have now set more suitable parameters. The first FFT bandwidth is 0.25 Hz. That means that the entire bandwidth is in the order of 1 Hz or so, because normally bandwidth is the 3 dB points. And I hadn't changed anything else. It is still 7 to 2 power 7, the bandwidth reduction. The total bandwidth in the baseband now is at about half a Hertz. And I have set the transform size to 14, and now it runs fairly rapidly, as you can see. It steps up each time a baseband transform is finished. I get several for the analysis of the sideband noise. And already now I see at 1 Hertz minus 108. And it will take some time before I get the result at higher offsets, but it will be much faster than it was before. But the ugly artifact is gone now. It seems I can read up to 350 Hz with these settings. So from below 1 Hz to above 350. And this is now 5 minutes, what you can see here. So I wait for a while and compare with the professional instrument. With X gain equals 8, it means the Fourier transfer bins are separated by 8 pixels, so the entire width of the peak is something like from here to here. That means that since this is a logarithmic scale and there is a straight line on the logarithmic, which means it is not a straight line in linear scale, and that means that points on the high side here get too large weight when the straight line is drawn like that, and that causes an error of nearly 1 decibel. And that's the price to pay when having a too small transform, which requires a too large X gain. But that happens only when the slope is very big, like here. Maybe it would have been better to run 15 and X gain 4. Anyway, what I'm interested in is at larger separations. The region from about 8 Hz or maybe 10 Hz up to 80 Hz is very noisy because of the high noise here that originates in the SDR-IP units. But I can read now, already after 1 hour, that the noise at 100 Hz is minus 143, 200 Hz minus 145.5, 300 Hz minus 146.5. And it may be easier to read if I make the x-axis factor even smaller. So here 200 Hz 145.4 and 300 146.6 probably. The differences are small except at 1 Hz, where there is more than 5 decibels. And the largest difference otherwise is at 100 Hz. And when we look at 100 Hz here, it's obvious there is a spur here of at least 1 decibel. So I think this is a fairly good agreement, except for the very lowest frequency, and I suspect that is something with the E5052B and not with my setup. Linrad is not limited to this. I can set this first FFT bandwidth to 0.01, which makes the transform 8 megabytes in size. And then I can set this first mixer bandwidth reduction to, let's say, 11. Now things are going to be very slow. And then I click at the frequency scale of the first FFT and set the lower frequency here. And that would be 9.999. Well, one more 9. And enter. And it's slow because it's thinking. And then I set 10.0001. Enter and wait, and then press apply. It's unhappy with the speed of the AD converter, but here we go. Here is the signal in the baseband, and now it is with size 11 here, but it is still the same filter. And I can increase this size, and that is a slow procedure. Well, it's obvious that it doesn't work right. You can see these oscillations on the noise floor. There was a glitch on the input. I had forced the DMA rate of 1000 long ago, and I forgot about that. I think that is not wise when running these very slow processes. So I change that is C, and minimum, let's say 1, and maximum, let's say 100. And it's a good idea to set the filter before clicking on the signal, because then this works immediately. No, it says limit is FFT1 storage time. I can do something about that, I think. X P storage time. I go up to 200. And now increase once more. And then reduce to like this. And I have to start the units also. I have a switch for the trigger input on the SDR eyepiece. And now I have to wait. Bandwidth 0.1, I have to wait. So I go to the main setup, and that is then a global parameter setup, that is S. Font scale 1, and I allow Linrad to block some cores if it wants to. And you can specify the screen size. I don't want to do that. And standard is... And I set process priority to 3, real time. Are you really sure? Yes. And no auto start. And then I save this. Now it looks better. It took 11 minutes until the first transform arrived. And it looks like this at 1 Hertz. In the order of 106 or so. And that is, in other words, without any correlation. After 2.5 hours, I have 86 averages. And I can see that correlation doesn't help at all here. The imaginary part is down here, 109, while the curve is at 95 or so. So I can read the noise from this graph, and I'm not really interested in that. It's the performance of this oscillator, and I don't have anything to compare it with. I can read the phase noise at 1 Hertz now that I changed the spectrum scale in frequency, and that comes at the same as before, minus 108, although statistics is not very good, because, of course, I have only 88 averages. I have connected a significantly better oscillator, and it looks like this after 45 minutes. At 1 Hertz, the noise is about minus 114, 115 or so. There is some frequency drift. It hasn't been running for many hours yet, so it will probably stabilize.
The baseband bandwidth is well below 0.1 Hertz, so I should be able to read the noise well below 0.1 Hertz here, and up to about 2 Hertz within these 12 hours I can get a fairly accurate level of the phase noise. I have changed the scales because now I am interested in the very close range from 0.1 Hertz up to half a Hertz or so. So I will save this graph, and then I will change the time constant in the phase locking between the two 10 MHz references, because if the locking is too fast, there will be correlated noise between the two SDR IP units, and that will destroy the correlation measurement. I have decreased the time constant in the phase locking between the two 10 MHz reference signals, and as you can see, something dramatic happens. If I compare with what I had with 10 times larger time constant, it's this. It's obvious that what I have here is a correlated signal of a similar level as the noise of the oscillator, means something like minus 72 dBc per Hertz. That is in antiphase with respect to the modulation that comes from the oscillator itself. So it is a correlated phase noise that is out of phase between the two oscillators, and exactly how it happens, I don't claim that I understand it, but I can observe it. And it tells me it's very important that the PLL time constant is long enough. Now, normally I run it at a factor of 10 above this. I have decreased in 2 steps of 3.3. I will decrease it some further to see what happens then. Here is the old measurement with the largest time constant. These strips mark roughly where the imaginary part is. And I switch to the present measurement. Here, this is with a 30 times faster PLL loop between the two references. And you can see very clearly that the imaginary part has been growing. So there is some correlation between the two channels that has been added. And it is visible from about 0.3 Hertz maybe. And here at very low frequencies, 0.05 Hertz, the imaginary part comes up here, and it's right between the uncorrelated curves. Now, the uncorrelated curves are based on only 3 averages. So it's a rapid thing. And very disturbing, at this point the real part is negative, the curve comes blue. So already here we can see that something has gone wrong, really wrong. And I change to show the original measurement. And it's similar up to about, well, above about this frequency. The yellow curves are similar. So it seems that the 30 times bigger time constant is big enough to allow measurements down to 0.1 Hertz with a good margin. And this baseband filter also. There is another way to check the phase relation between the two channels. I'm using here in normal processing mode the S-meter graph. I have set the amplitudes equal and then misadjusted the phase so that there is only about 15 or maybe 17 dB difference between the two linear combinations of the signals. And I set a mark here by clicking outside. Means there is no signal. And then I click on the signal again to come back. Now I have two marks on the S-meter graph, like that, about 3 centimeters. And that corresponds to a time 12:47:05 to 12:50. So that's about 3 minutes. And 1 centimeter per minute, it's the order of the x-axis. I haven't made any time scale on this graph. The PLL time constant now is 30 times faster than normal operation for correlation measurements. So I will restore the normal time constant now. Here we can see an oscillatory behavior on the phase difference between the two reference signals. Time between peaks about this. That is something like 4 minutes or so. Means a very low frequency. That is 240 seconds. So it is 4 millihertz. It means that frequencies above this resonance are well suppressed. Means the oscillators don't correct each other at frequencies at times faster than 20 seconds or so. Means measurements should be perfectly accurate down to 0.05 hertz or so when it comes to the phase to the absence of phase correlation between the two. I have connected a significantly better oscillator. This one. I compare it with the Wenzel oscillator, which I have saved here. And you can see it is a big difference. Now, when I look here, I see there are problems. Firstly, channel 1 is not as good as channel 2. That is the oscillators I'm using as references for. But the big thing is the imaginary part, which is down here, goes up and comes to the same level as the real part, which means there is a correlated signal between the channels, which is in 90 degrees or something, and that should not be the case. It means there is correlated noise between the two reference oscillators. And as I have studied the PLL loop, it shouldn't be because of phase locking through the loop. Maybe it could be pulling between the oscillators if one sends some signal into the other. Or it could be something that I don't understand yet. I have changed the scale factors to make them more appropriate for this situation. And you can see the correlation gain is this much, but here it's only half as much. But from the real part to the imaginary part has grown from here to here. So up to maybe 0.4 hertz, the problem is not strong. But at 0.1 hertz, there is a significant problem. But the baseband filter is narrower, or it is about 1 hertz. So problems because of this should not occur, I think, at this level. As it turns out, I had forgotten this capacitor and how the loop filter was designed. This capacitor makes the low-pass filter together with these resistors.
I had forgotten to put it back some long time ago, and I don't know exactly when. Anyway, the reason why it's sitting on the oscillator is to avoid a potential difference between this ground point and some ground point inside the box. These switches are inside the box where this op-amp is. And magnetic fields means 50 Hertz is present always, and I don't want that to couple into the LO. So the only regulation I had was these resistors with this big 10,000 microfarad capacitor. That reduces the PLL loop gain when the time constant is set large. That is in order to avoid oscillations in the PLL loop. So when I thought I was removing the PLL at low frequencies, I simply just reduced the gain. And that made some significant difference. But now with the capacitor in there, the gain at 1 Hertz is very low.
I have changed the scale factors to make them more appropriate for this situation. And you can see the correlation gain is this much, but here it's only half as much. But from the real part to the imaginary part has grown from here to here. So up to maybe 0.4 Hertz, the problem is not strong. But at 0.1 Hertz, there is a significant problem. But the baseband filter is narrower, or it is about 1 Hertz. So problems because of this should not occur, I think, at this level. This is the screen after 41 hours. So statistics is fairly good. And I can see there is some small improvement at 0.05 Hertz. The imaginary part is below the real part, but they are very close to each other. So this is not reliable. It doesn't show the phase noise. And of course, this bandwidth is about 1 Hertz, if you look down here. So I shouldn't expect a good result below 1 Hertz. And as you can see, at 1 Hertz, there is a problem. There is a negative contribution in the real part that cancels some of the positive. So there is a dip at 0.1 Hertz. And also the imaginary part is much stronger than what remains of the real part. And the imaginary part, that's the square of the signal. I will change scales to see better, but before that I will compare with the curve I have saved. Here, this is the Wenzel oscillator, and you can see that it is very different because the noise of the oscillator is dominating. So already at 0.1 Hertz, it looks like the curve is showing the oscillator performance and not the system performance, as we have here. With these settings on the x-axis, I can see that the distance from the real part down to the noise in the imaginary part is about 10 decibels here, in this region up to about here. That's where the results start to become inaccurate, at about 0.25 Hertz. Looking at the baseband, you can see that the signal has drifted to the edge of the filter, which means that the noise down here enters into the mixing process. Maybe that explains the problem I'm seeing, I'm not sure. Or maybe it is a correlated noise contribution originating in the SDR IP. Because now I do not think it is possible that the oscillators convey correlated noise through the PLL. I changed the settings on the axis, 0.1 Hz here and 5 dB per division, and we can see how the imaginary part comes high above the real part. So we can guess that this is actually the phase noise, but it is phase twisted. Means I think this is actually a problem caused by the filter that is extracting the carrier used for the demodulation process. So I will save this. The biggest problem I see is the difference between the two channels, more than 10 decibels from here to here. I have decreased the baseband filter bandwidth by a factor of 2, and I intended to see whether that makes a difference. And it seems so, but it's already 11 hours. And I have problems, occasional bursts of noise. So at this point I made a change. Here the big yellow capacitors, 47,000 microfarads, together nearly 100,000. I replaced one of them with this blue one, which is 220,000 75 volts. And that caused a severe degradation. You can see the noise trace here, how narrow it is, and now it is much wider. I think this is because of leakage currents through that capacitor, which is brand new. So I wait for a while to see whether the leakage current decreases and if it possibly becomes better than before. Originally, the noise at 0.1 Hz was about 15 decibels higher in channel 1. Now, after 20 minutes, at the same separation here, it is about 30 decibels higher. And it looks like this on the main waterfall. So if it helps, I will have to wait a long time before this stabilizes. This does not look very encouraging. The old performance with the old capacitor is down here. It's blue starting at this point, and it narrow like that, the white region. Now it looks like this, and in the main waterfall it looks like it is staying constant with time. But this is 1 hour only, from 11:20 to 12:20. So maybe tomorrow. Waiting for this capacitor to become stable will take a long time. I'm running the first FFT waterfall slowly, and you can see it reduces slowly. So it's a matter of many days. I have replaced the big capacitor with one of these, 120,000 microfarads. I have restored the original speed on the waterfall, so this should be compared to this. And this is immediately after replacement, so this looks a little bit promising. The capacitance on the supply voltage for channel 1 is now 5 times bigger than originally, while the capacitance for channel 2 is about twice as big as from start.
The frequency is drifting a little up and down while Linrad is collecting the average of many correlation spectra. Each time the frequency is corrected, there will be a white line in the waterfall. That is a big glitch, but during that time Linrad will not collect the spectra, because of course it knows when it is going to adjust the frequency. I have changed the 0 point of the waterfall from 20 to 100, and now one can see easily what is going on. And the drift has changed direction because we are getting into the evening and it's getting colder. I can get the correlation gain from the uncorrelated spectra down to both the imaginary part and the real part, because both are the same here, where the noise from the object under test is not contributing. And then when I go here, we can see the noise from the oscillator under test, while the imaginary part stays the same all the way somewhere around here. So I will expand the scale. And here it is of course the same. I go from the magenta trace down to the imaginary part, which is the noise level of the imaginary part. And here something happens a little bit above 0.15 Hertz, and here again, and then suddenly there is a dip in the real part, means there is an error signal of some kind that has the opposite sign as compared to the noise from the device under test. And the imaginary part is low at this point, but it's equally strong. So something goes wrong. There is definitely a contribution from a undesired signal which has not the correct phase as compared to the expected. It means that I could say it's safe up to 0.2 Hertz, but at 0.15 there is a problem. Now the saved spectrum I have here, which I made with twice the bandwidth of the baseband filter, it has more correlation gain because there is about twice as many spectra. That's 1.5 dB or so. So rather than what I had now was 15 dB, a little bit more, I should expect something like twice as many, 1.5, say 17 dB. That's about here. And when I look at it, I cannot expand this because I didn't save like that, but you see it comes. But here at about the same frequency, now here maybe 0.2, there is the same problem. This dip is not at exactly the same position. It doesn't look exactly the same, but certainly what I see here is not correct. So the conclusion is it's not caused by the narrow filter in the baseband. It is a real signal caused by some programming problem that I don't understand, or maybe by some interference in the SDR-IP units. They are running synchronously because they have the same 10 megahertz reference, both of them. And well, it's not exactly the same, but when divided down to do the digital stuff inside. Maybe. I don't understand it simply, but it's a lesson to learn. It doesn't help to make the baseband filter infinitely narrow, because other problems pop up, or may pop up. But what one should do is to look for the imaginary part as an indication. It should be low, and it should be the same everywhere, except on spurs if they occur. So when something goes wrong, it can be seen in this kind of spectrum graph that I'm showing. At close range, the noise from the SDR-IP 80 MHz oscillators gives a significant contribution. So I have now changed to use sound cards instead. That makes the noise of the device under test very close to the noise that I see without correlation, the blue trace here. The magenta trace is a bit higher because that oscillator is not quite as good. But you can see the imaginary part is about 10 decibels low up to about here when things go significantly wrong. And it's the same, it's about 0.125, so let's say 0.15. That's the lowest frequency where my system works. And now there is no SDR-IP involved anymore, and this filter is very narrow, so it's not signal coming through the filter. And the conclusion must be, this is because my oscillators couple to each other, one way or another. I don't think it is through the cables, because I checked the coupling through the cables and it's less than minus 100 decibels. But maybe that is too much to be free of pulling. I really don't know, and it doesn't really matter because there isn't any need to go as close in as 0.1 Hertz. So I can stay at, let's say, not closer than 0.2 with this system. This is with the sound card after 10 hours. And as you can see, the desired signal, the real phase noise of the object I'm testing, this unit, is nearly noise-free. It is more than 10 decibels above the random noise, up to 3 Hertz, and I get an accurate enough reading at about 5 Hertz. I cannot go to very high offsets because I have this problem up here. The 10.0, that's DC, and there is 1/F noise in the sound card. So the limitation when using the sound cards is I can see only very close spacings. But with the SDR-IP I can see nicely above 10 Hertz or so. And when I expand further, you see the ugly structure here. It is this noise together with the second harmonic which we have here. And the sound card is useful up to about 6 Hertz. That is this sound card. It's a M-track quad from M-Audio. So here is the setup, the SDR-IP units and the M-track quad. And then filter capacitors for the oscillators and for the M-track quad. These are the reference oscillators. Maybe they couple somehow. The boxes are fairly well closed, but still I need a very high attenuation to avoid pulling between them. And then this is mixers and other stuff. And here's the system I'm using. Local oscillator, 10 megahertz, one here and one here. Amplifier, and that is isolating a little bit for signal coming backwards. Then there's a coupler to send this reference to the SDR IP. And then a coupler to pick out the signal and then attenuate it to not get back from the other oscillator. So 10 megahertz goes this way into a mixer, and also from this oscillator this way into the same mixer. And from the mixer there is some signal of this frequency coming out in the other port. And this amplifier is isolating reasonably well, and there is 30 decibels here, and then there is this coupler. So the signal from here is attenuated by over 100 decibels before it reaches this point. The oscillators feed a hybrid here and a hybrid here that splits into 0 degrees and 90 degrees. A hybrid that splits it into two. And then the signal coming from the device under test, it's split with a hybrid, and then it goes through a filter and a coupler that picks up a signal and sends into the SDR IP, and the rest of the signal goes to a stepped attenuator to set the level properly, and into a 90-degree hybrid that splits into I and Q when it is mixed with the local oscillator here. So I get I and Q from channel 1, and the same way from channel 2, an audio amplifier and the M-track quad. And the units, both the SDR IPs and the M-track quad, are modified to give them the performance required for this kind of measurement. In this video, Nerds 82, you can see what I had to do to make the SDR IP units suitable for sideband noise measurements. This video, at this time, it is Nerds 81. It contains some information on what I did to the M-track quad. It is modified by putting the signal straight into the AD converters with a capacitor and a resistive voltage divider to set the level to fit my system. And there are some other things that you will see if you continue from this point. It's a fairly long video, and it shows how my UADC4 stopped working properly, and I had to find a replacement in order to see at close range, because that's the primary interest from my side, to make the device under test that you have seen that I'm using now, to make it a little better. That's not so easy because it's reasonably good already.